So let's get started. Eric, we might get started. Okay, so brief introduction, who we are. So my name is Raphael. I'm the one of the tutors at Complete. So we started this 6 years ago. We only specialize in tutoring VCE Physics. Really, the goal is to have an environment where all the tutors, right, every single person in our team, we absolutely love physics, right? We're excited about physics, and we want to create an environment where we're really good at teaching physics so that students really enjoy and prosper. And we've taught more than 500 students over the past 6 years, all of whom have achieved very good results. Pretty much a lot of people above 40, majority of our students get above a 40 raw score, so we do very well. And yeah, so my day job is I'm a final year medical student at Melbourne Uni. And yeah, that's what we do on the side. And yeah, welcome to Complete.
Yeah, I'll take it over, Raf. Hi, everyone. My name is Eric, and I'm a VCE teacher, as well as the GM of Complete VCE Education. I actually talked to some of the students in my class that I've been doing physics for 10 years, ever since 2015. I started my Bachelor's of Science and doing enrichment stream in theoretical physics. So if we count the years now, it's been 10 years I spent my time doing physics and physics teaching. Very passionate about teaching as well. Combined total 6 years plus in school and tutor experiences. And currently I'm a teacher, in a high school in Victoria. So I'm doing the daytime job as a teacher and tutoring on the side as well. So hopefully today I can share some of the insights to you about what teachers may want to know, want to ask, and you can get both sides from the exam prep perspective and from the markers examiner's perspective. And Asel, who's the head of resources, he will be joining us, but he's actually joining us with the questions. So he drafted all the questions, he wrote all the solutions, and he got a very, very good ATAR with a 50 raw in VCE. And he's working as our head of resources now, so he drafted alongside with me all the questions for today. So hope you guys will enjoy it,
100%. Yeah, so really what we're going to be covering through today, and we'll get started very soon, guys, is really going over your SAC-2 preparation. So it's a final revision for you guys. I know most of you guys have your SAC-2 fields in May. So most schools have it mid-May, some May 20, some a bit earlier. Some schools even have it April, end of April. That's why we're running a bit earlier, so that you guys get a bit of a head start, a bit of a taster in terms of what the common types of questions, right? Common questions, as well as what the hard questions or differentiated questions could be like in the SAC. So as part of the SAC, you'll receive a few things. Number one is handouts. If you can't copy everything down in time, feel free to take a picture, or just don't worry about it, because we'll be sending out an email with all the question resources and the solutions to summarize this webinar via email after this webinar. And also, we'll send out this Mock SAC with the solutions, a formula sheet for Fields U3A2 for you to take into the exam for the SAC, as well as a summary sheet, right, that lists out all the important things or the main points to know in terms of templates to how to answer, some of the explained questions, as well as the key summary points that is the most high yield for the SAC. If you guys are new to Complete and would like to learn a bit more about our program, then feel free to schedule a 15-minute free consultation as well. Eric's going to put a link in the chat. So really in the 15 minutes, we'll be answering some of your concerns, right? So maybe some of you guys haven't been doing as well in physics, right? I know a lot of our students in year 11, you do okay. Year 12 gets a bit harder, right? So if you're not performing to the level where you want to perform, or maybe you're trying really hard, right? You kind of understand all the concepts, but pretty much every single SAC, you don't do as well as you want. We're here to provide you with the discipline, with that push you need, right, to do very well in your SACs, okay? So yeah, that's there, and feel free to subscribe to our email mailing list as well. All of our resources, including notifications for webinars such as this, our blogs for concept explanation videos, and other resources, our notes and our mock SACs, things like that for the rest of the year. We'll send through our mailing list. So if you'd like, we've got like a website link as well in the chat. You can scroll to the bottom of that page. We've got a card for you to submit your email so that we can send through relevant resources for you guys for the rest of the year.
Fantastic, Raf. So without further ado, let's begin our webinar today. So we got two parts. The first part, I'll walk you through about the advanced thinking multiple choice questions, which is the ones that are the hardest, the trickiest questions you may find in your SAC. And I'm not making things up. This is from actual SAC that's been showing before, provided by our students, and the things that probably will encounter in your own SAC. And so we provide you some guidance with that. In part two, Raf is going to walk you through the high yield structural questions, which is the ones that we're emulating the actual VCE papers. So to get insights from that. And the questions are all written by us that we will show you, how we'll gain the course in VCE Physics. So you get two parts, right? The first part is written by myself, the teacher insight. So what exactly are the teachers trying to ask and what they're trying to find out from you? How do they gauge if you get, a good score or bad score? What do we see? And the second part is the raw 50 mindset. How do I approach questions like a top scorer, like a cell, who got raw 50 in physics? So we have these two insights and thinking for each and every question we have in today's session. So once again, final reminder, I know we had the same experience during the pandemic, during the COVID times that we're going to do online lessons. So I always encourage the students, you actually learn better and you will be more engaged if you get your cameras on. You don't have to get your face. You can get to the wall or something. But if you turn the camera on, it's a sign that, you're very happy, well, you are committed to learn something today. So I saw actually some of you got a camera. So no, Megan, appreciate that. Thank you very much. So if we got more of that, that'll be fabulous, right? To see your faces, which is actually much I preferred, as a teacher. So let's keep that going. I'm sure more of you guys will turn on the camera as we go through. Here comes the first question. All right, so there are no diagrams. So I think the first thing you could do is to draw some diagrams as we're going through the question. So the context is there's a planet 55 Cancri E, very weird name, has double the mass of Earth. A spaceship is hovering at a distance of 2 times the Earth's radius, RE, about the Earth's surface, which is RE is the Earth's radius as given. The question is asking you, at what distance from the center of that exotic planet, in terms of RE, would the spaceship experience the exact same gravitational field strength as it does as 2RE about the Earth's surface? All right, a bit of a mouthful of words, so you want to draw and sketch diagrams. So Ralph, let's give everyone, let's say 2 minutes to think, draft, and try on the question. So you can see there's a timer going on. All the best. And if you've got any questions you want to try to answer, feel free to private message us. All right, we will ask everyone to send out your answers to the public once we hit the timer at 2 minutes. But before that, if somehow you manage to figure out the answer or you want to make a guess, then private message either me or Raf so we can see what you have written. All right, about 30 seconds left. So if you've got some insights, if you want to share ideas with us, please type out your answer. We got some messages already. Okay. Thank you, Kim. And thanks for sending to everyone. That's more interactive and hopefully you can bring, more of us today into physics. So, all right, 5 more seconds. It's time to share your answers. Let's see. I always love the sound effect of the timer. So thank you, Uma. Thank you, Ved. We got 3 yeah, 3D options so far. And how about others? We got about 65 people today. That's quite a lot, that's quite many people joining us today. So if it's still puzzling, still trying to find out why the answer might be D, well, let's go to the walkthrough. Okay, this is what I did. I drew a diagram, simple as that. So the idea is you always want to look for the keywords in the question, right? So if I'm the teacher, I set the question myself. Here are some things I want to tell you guys, what's behind, behind the scenes. So the first things first is the word that I use, right? About the Earth's surface is something that is deliberately put onto this, right? Has double the mass of Earth also, entails that you're going to translate that into mathematics, which is a skill that we, cherish in physics student. So, most importantly, if you're SL, the most important thing you pointed out is that we always want to draw a diagram, but not any ordinary diagrams. We want to draw something that always get the distance from the center of mass of the particular object that generates the field. So not about the surface, you want to get from the center of mass of objects, because this is how field strength is calculated. We measure the distance from the center of mass of one thing to a particular position. So by doing this, you can avoid making silly errors like substitute the wrong values in your answer. As precisely, how are we going to do this? Well, step one, you're going to figure out the gravitational field strength 2r above the Earth's surface and express, with the unknowns that we have. You don't really need to sub in the mass of Earth, even though it's given in the VCE paper, in the data sheet. The radius also given, but we don't need to do that. And the reason why is because you can simply do an algebra, right? Use algebra to solve the question. So I just annotate here so you can see. The first thing is to write down the formula, right? That won't give you any marks, but that's a very good step to do. And you can sub the values in, which mass of Earth is just me. And then the distance is 3 times the radius, not 2, but 3. This is what get the most students, right? A lot of them put 2RE instead of 3 because they read the question, says 2RE, and they identify that as the distance where we do the measurements. But cells say, no, you can't. If you look at the diagram, it shows very clearly the combined length is 3RE, right? This is to avoid making silly mistakes and errors. And if you do this correctly, I think you're halfway to success. So yeah, be careful, as what we have discussed before. Now, give me some time, just remove all the drawings. There we go. The next step is to figure out what about the field strength above the exotic planet. So first of all, we set the unknown R as the length between or the distance between the center of mass of 55 Category E to the point of measurement where the rocket is locating or the spaceship. And so we can figure that out that instead of putting ME, we put 2 times ME because it's 2 times the mass of Earth. And R is just the unknown. We're trying to figure out or express R in other terms that we have. Which brings us to step 3, right? So above the Earth's surface, we got G equals to GME divided by 1/3 squared. So put 3 squared times RE squared. And in that particular position, it's equal to 2G ME divided by R squared, right? So these two gravitational field strengths, they're equal. So we can equate them in this equation here, right? If you see this, you can simply cross out, right? You can simply cross out the duplicates, right? You got ME on both sides, we cross it out. You got G on both sides, we cross out as well. And after some algebra tricks, you can simply rearrange the equation and get R squared equals to 2 times 3 squared times R2 squared, right? And if we take the square root on both sides, you would get nothing but R equals to 3 times square root of 2 times RE, which is D. Most of the students who answered who got correct. All right, so fabulous job to those who give it a try and got the answers right. And I hope you did that with the the correct mathematics, right? And some tricks you may take away that makes you speed things up, right? Because in reality, with the new syllabus, right, the total questions in VCE or the total marks will be 120 rather than 130. But then the density of the questions, they get a bit harder. They also get a bit more complicated. So if it took like 4 minutes to do this question, chances are you may run out of time when you get to other sections. So ideally, you spend 1 or 2 minutes within to complete question 1. That is the ideal. So hopefully there's some tips and tricks you can take back home from me and from myself to get good in Fields. Okay, so I'll take a pause here in case you want to take a screenshot, but just to be aware that we will send out all the materials, including today's recording, after we get that rendered and processed, say 2 days from today, we'll send it out and to make sure everyone receives it. So be my guest, you want to take some pictures, but don't be panicking if you don't get everything today. So I'll pause here and ask any questions from the audience or any things you want to clarify before we move on. All right. So fabulous, Raf. I think we can stop the timer for now and we can start a new timer because we've got a new question coming. Okay. Fabulous. All right, let's go to question number 2. So this one, without much explanation, just want to say this is a cross section of a loudspeaker. If you chuck it, just cross it and you cut it open, you can see that the magnet is shaped something like this. So originally it's like a spherical shape. It's like a cone. Inside that there's another magnet. So there's a north and south, right? And they should be connected, by the way. So good luck drawing that. So over here we got the north and south poles, and the question is asking you if the current flows through the coil in what's shown in the picture, what direction would the coil initially move? Okay, so there are 4 options: left, right, upwards, and downwards. If you know the tips and tricks, you can answer that in 30 seconds. But today we'll give you guys like 2 minutes to give it a think of the question. And I want you to reason why do you think it's such a way? Why do you think, let's say, left is the correct answer? Or you want to argue your way out? So take your time. You can write down the correct options. You can talk about the reasoning as well. So, and this one, I really want you guys to turn the cameras on because we can. There's one thing I want to teach you, and I think that's going to be taught better if we can see at least nothing but your right hand. So I may be spoiling a bit here, Raf. A bit of a hint. Yeah, thank you, Hasha. Good to see your face. Hey, how are you doing? Julian and Mohammed as well. Appreciate that. That's good. All I need is your right hand. All I need to see is that to see if we got this question correctly. All right, start to get direct messages. So make sure you PM the message, And this time we got some variations. So rather than just one answer, I got multiple. Okay, let's spend about 1 more minute to think about the question and to jot things down. So it doesn't matter which option you pick. I want to see your thinking. Like, how did you arrive to that particular option? Yeah, fabulous. We got no A's so far. That's a good sign. That's a good sign. No one picks A. So B, C, or D. Okay, counting down to 10 seconds. If you want to send your answer to the general public, please do that. Put your answer, not private messages now, but send it to everyone if you may. And I'm going to hit the timer once again. Okay, well, this time, when we got different answers, it means that the question is inherently challenging. It means that it's have value to investigate, what the question's about. So let's have a look. Let's have a look. The teacher insights is to apply the right-hand palm rule in something we've never seen before, right? In unfamiliar situations. This is not very straightforward. Unlike the questions we see on textbooks unlike the ones we see in like the past papers. This was a bit exotic. And the way we apply the palm rule is a bit interesting. So I'll talk about that. For a sales framework, what do we do? 3 steps. You're just going to identify directions of B field, right? Of the magnetic field, where's it pointing toward? And then the direction of current. And afterwards, you apply the right-hand palm rule. So that is the way we do it. Without further ado, let's get into the solutions. So first of all, I want to frame our discussion because this is a whole magnet, right? It's a big picture. So we want to pick a particular point where we apply this right-hand palm rule. So a sales saying we can consider, actually I don't want to spoil that because I want to ask some questions with you guys have shown your faces and be happy to participate today. So maybe I will start from Julian. Hey, Julian, if I say pick on this point, see if I can draw this clearly. Let's say about here. Okay, so this is the part where the coil starts wrapping into the page, I'm not asking about the current direction. In fact, I want to ask you, what is the direction of the magnetic field at this particular point? Yeah, just going up, right? It's nothing fancy, right? Always from north to south. So the B field always points from North Pole to South Pole, right? So it goes upwards, and that aligns with what a sales thought, right? So if I zoom into this part, the B field, and this time we will just use our 4 fingers to show the B field because ultimately we're going to find a force, right? So fabulous, well done, Julian. You found out the correct direction of B field, and let's move to Mohammed. Mohammed, I got another question for you. So in this case, it's a bit hard because it's hard to draw 3D and 2D pictures. What is the direction of the current in this case? How would you describe it?
Our jets are going into the page.
Into the page. Exactly. I mean, it doesn't seem like into the page because if you draw the current, let's say here, it goes like up. But what it's trying to show here is actually the current goes like this, right? It goes into the page, it comes out, and it goes into the page again. Hope I'm making sense of what's happening here. It's just kind of wrapping around the magnet. So fantastic. It is going into the page, and that is nothing but the current. All right. Now, last but not least, Megan, you're the first person to turn on the camera, so I want to leave this review to you. What is the force direction based on the discussion so far?
To the right.
To the right-hand side, that's where the palm's facing. So fantastic. The way I want to talk the rule is called the right-hand slap rule because when you do the slap motion, you apply the force in the direction where the palm's facing. I think that's more intuitive than palm rule. Palm is like you hold something, but slap, you get the force into the picture. So yeah, to the right-hand side, that is the answer. Fabulous. So for those who answered B, congratulations and well done. Right. For those who tried the question, good effort. Keep up the fantastic participation today. And one last thing before I pass it back to Raf to go through some of the harder questions for today is that most of you think this is a 25%, one of the 4 options in this multiple choice. If you truly understand, magnetic forces, this should be a 50-50 because the rule about magnetic force is that all 3 vectors, B, I, and F, have to be perpendicular to each other. Okay, so if 2 of them goes parallel, let's say B and I are parallel, there will be no force, all right, induced in the picture. There'll be no forces. So the golden rule of thumb is has to be perpendicular. Okay, in other words, these 3 things cannot share the same direction, or at least in the same axis, if you know what I mean. So if we concluded that the B field is pointing upwards, it means that the force, right? If B field is upwards, it means that the force cannot go upwards or downwards. So you eliminated 2 options straight away. And all that's left is to determine if it's going to the left or to the right-hand side using the right-hand palm rule. Okay, so hope you have learned something here, some tips and tricks, and the proper way to apply the right-hand palm rule in different situations. So because of due time, I want to make sure everyone gets the chance to try some structural questions. I will pause my part here and move back to Ralph. Happy to have you take over from this point onwards.
Great. So very well done, guys. And thanks to those who turned the cameras on. It's great to see some faces, and thanks, guys, for your contributions. It's amazing. So MCQ is over. We'll skip through a few of the easier questions that I believe are a bit easier, but standard. We will send out the webinar handouts to you guys after this webinar, and you guys can go through some of the more standard questions in your own time. I think it's better use of our resources to go through some harder questions. That's exactly what we're going to do from this point onwards. So some of the short answer questions get pretty hard. We'll skip through question 1, which is a gravitational field distance graph question, which I think is, again, pretty standard. So we'll skip that one. Do it at home, guys, to get some good practice. And we'll move on to question 2, which I think is a great question. Okay, so let's take a read. Okay, question 2. 2 particles are emitted, right? So you look at the diagram, there's 2 particles. Okay, particle number 1 is particle A. So it's this guy over here on the left-hand side. You've got particle B. Okay, particle B is this on the right-hand side. Okay, so we'll read the question. So they're emitted at the same time from point P. So point P is this point in the middle. So 2 particles coming from the same point, they get emitted at the same time in a uniform magnetic field. So this B field, okay, is are these dots right here. So these dots is your B field. And if you look closely, if you zoom in and you look closely, these fields have a cross. Okay, it's got a cross. So what that means is your field is going into the page. Okay, I'll elaborate on that in just a second. So particle A now, it says it's got a charge of 2e. Right? It's got a charge of positive 2e, okay, and a mass of m. Okay, so particle A has a charge of 2e and a mass of m. Particle B now has a charge of negative e, so it's negative. So it's got half the charge of particle A, and it's got a mass of 2m, so double the mass of particle A, but half the charge and the opposite charge. They're both emitted with the same speed. That's important. So the same speed. And the question is, which one of the particles will return to point P first? Obviously, particle A is going to do a circle. It's going to go clockwise, okay, and come back to the same point, point B. And particle B, I'll use a different color, okay, it's also going to go in a circle. It's going to go anti-clockwise, in fact. So it starts going to the right, does a loop, comes back. Which one returns to point P faster? Okay, that's the question. So I'll give you guys the hard questions. I'll give you guys 4 minutes, and I'll start the timer now. And again, if you get the question a bit earlier, message me privately or Eric your answer, and we'll give you guys some feedback. So good luck. Okay, so we're almost halfway through. I think a few of us are giving us some answers, so some pretty good answers. I think that's good. I think we can work on in your answers, your explanation. So how do we explain it a bit better? So I think some of you guys got the right idea, but we can make the explanation a bit more comprehensive, right? So I still haven't gotten a perfectly comprehensive answer yet. So I'll give you guys another 2 minutes or so, okay? And we might give you, and Eric might give you guys a hint in a little bit to give you guys a push. Yeah, 2 more minutes. Good luck. A final minute or so left. We just pay attention to make sure that you've included everything into your consideration. So that includes your charge. You want to look at the charge differences between the two particles. You want to look at the differences in their masses, right? And you want to think about really what is the factor that you want to focus on to get a very beautiful and elegantly solved result. So 30 seconds or so, and we'll get started the walkthrough.
I just want to chime in for now. It seems like lots of you are applying the formula R equals to mv over qb. This one's very tricky because something about the force is also affecting. So I'll have Ralph explain this to you all.
Cool. So Eric, if you don't mind moving to the next slide, we'll go through the answers. So yeah, let's go through, two things. The first one is what exactly are we trying to test you guys in this question, right? So from the teacher's perspective, we're really looking at your understanding of a few things, right? So the first one, I'll use a different color actually, is what is the variable that you guys are being tested on? So I think in the comments, a few of you guys were using the formula I equals mv on qb and talking about the radius. So a lot of you guys focused on the radius. Whilst that's okay to focus on, right? The radius is fine to focus on. There is a better and more fundamental focus or symbol that we can focus on to get a better result. And that is the period, right? Everything in this question, guys, comes down to period. Okay, I'll get to that in a second. Okay, and the second thing that we look for, guys, is not just whether you understand it, can you explain it elegantly in a short answer, especially for these explain questions, right? It's never easy in physics. These are the hardest ones, so we'll walk through that later. And in terms of the approach, the best approach is one that addresses period. You're comparing period between particle A and particle B. Okay, and so to do that, you have to derive a formula that has period as your subject and also factors into account the differences in mass, differences in charge, as well as your magnetic field strength. Okay. By the way, I think Eric told me I made a mistake here. The particles, if you do the right-hand palm rule, they actually orbit, I think, below. So they're doing circle below instead of above. So a small thing doesn't really change our question. Okay, so let me clear the screen and let's walk through how do we derive the formula for period. And we can start with our, very famous equation that we all, I think, were using, and that is just our radius of a charged particle in a perpendicular magnetic field equation. So that's your R equals mv on qb. Okay, so you can start with this one. That's your first equation. Okay, And you can use another equation as well, right? So the second equation we can use, and this one is a very useful equation that's simple but often overlooked, right, in the fields as well as the motion area of study. And that is the formula for the velocity or the speed of your particle going in a circle. So the velocity of your particle is given by a very simple definition, right, which is distance divided by time. So distance over time. And I'll pick on some students here, right? So you're traveling circles here. So you're going a circle. Let's pick on maybe Mohammed. Okay, Mohammed, why don't you tell me the distance that you're traveling when you're traveling a circle? What is that called? What do we define that as?
The circumference.
Just the circumference. Good, right? So velocity is just distance over time. So the distance is just the circumference, which has what formula now, Mohammed?
2 pi r.
Good, right? There we go. So your velocity is really just the circle, which is the distance or the circumference, which has the formula 2 pi r. So the velocity is 2 pi r divided by the time it takes to travel in a circle. We'll stick with you, Mohammed, right? A distance, the time it takes to travel one circle, there's a name for that. What do we call that, Mohammed?
That's the period.
Just the period, exactly. A period is the time it takes in seconds to finish one cycle or a circle. So we've got our two equations now. We've got R equals, so let's write it on the side again. R equals mv on qb. We've also got velocity equals 2 pi r on t, okay? And now what we can do here is we can sub our second equation, substitute that into our first equation. And what we get is this, right? We can do the algebra here. R equals m, and in brackets, we'll sub in our velocity here, which is 2 pi r on t divided by qb. Okay, so once we've got this, we can start to simplify. Now, we know that there's an r, a radius on both sides. So first of all, we can cancel that out to make it a bit cleaner. So let's cancel out the r on the left and the r on the right. And we're left with just this here, okay? So now we can fix it up a little bit by moving the qb to the other side, the t to the other side. So that gets us qb t equals 2 pi m. Okay, so we've simplified a bit now, and now we can get an equation for the period, which is t equals 2 pi m on qb. And that's your formula, right? An important formula here for the period. And now we can take a look at how this formula applies to both the period of particle A as well as the period of particle B. So for particle A, okay, the period TA, we'll use this equation here again, okay, is equal to 2 pi. Now the mass of particle A, recall guys, is just m, right? So the mass of particle A is just m, so we'll just sub in m here, and that's divided by qb, so we'll put in the charge. The charge is actually now 2e, we'll put in 2e. So 2e multiplied by b, your b field's the same. Okay, so we get 2 pi m on 2eb. And you notice there's a 2 at the top and bottom, so we can cancel those out, and we'll get pi m on eb. Okay, so your period of particle A is pi m on eb. So keep that in mind. We'll come back to that in just a second. So now in particle B, the period, let's calculate that. Period, again, we'll use this formula here, equals 2 times pi times m. So the m, remember guys, particle B has double the mass. So now we sub in 2m, okay? And then we divide by q, which is the charge. The charge of particle B is just e. So for the purposes here, we don't care about the sign because we care about the magnitude to calculate the number for the period. And the charge is just e, right? So just one e, and then the magnetic field B field has the same value. So we simplify everything, and we actually get 4 times pi m times eb, okay? And then you're like, wait a second, right? This identity here looks very familiar. It's familiar because it was the identity for period of A. So what we can say, therefore, at the end is the period of B is 4 times the period of A. Okay, so we can conclude by saying that, okay, since the period, which is the time it takes to travel one circle, is 4 times bigger for TB, particle A finishes a lot faster, so 4 times faster. So a lot of you guys gave me very good answers. I think if you stuck to R equals MV and QB, and then linked that to the fact that, you know, one has a bigger radius or one has a smaller radius, and how that would affect arrival time, I think that's fine. But a better answer would address period, which is the fundamental quantity that we're looking at here. So Eric, now, if you don't mind going to the next few slides, we'll just explain everything again so that you can look at our working. So here's what we'll write. We'll write part A, okay, returns to the point P first. So 4-mark answer, start by answering the question. And the next thing is you can talk about the derivation like we showed above, starting with these 2 equations, simplifying to our main equation. That gets you 1 mark. Okay. And then finally, finding the periods, right, for TA and TB. And then at the very end, summarizing by saying that the period of A is going to be a quarter of B, therefore it comes back a bit faster. Okay. So are there any questions from anyone so far with question 2? Okay, I'll take that as a no. So good. Let's move on, Eric, to our next question. So that's question 2 done. One more question and we'll call it a day. All right, question 3. So you've got 2 light aluminum tubes, A and B, and they're supported by a vertical wooden rack as shown below. So you can see that both of these aluminum tubes rest horizontally on wooden pegs. So these triangles that you see here, these like wooden pegs. So just got 2 aluminum tubes resting on there. The 2 thin light aluminum tubes form a parallel circuit with the DC supply. It was observed that one of the tubes jumped upward, okay, when the DC supply was turned on. Identify which tube jumped upward and why this occurred. So this one, I think we can give you guys 2 or 3 minutes to have a try. So I'll start your timer now. And once again, good luck for this one. Okay, we've got a minute and a half remaining, guys. So give you a bit of a hint. So we know that the right-hand side is positive, left-hand side is positive. So the current goes in an anti-clockwise direction. Okay, so another minute or so, and we'll walk through this question together. We're getting a few answers now, so I think a lot of you guys got the right answer. If you can also write maybe some brief points to explain how you came about to your answer, that'd be great. Try not to forget one key element that we'll have to implement as well when explaining this. So anyway, we'll go through all that later. So yeah, a few more seconds. Cool, very good. So I think quite a few of you guys got the right answer. What we really want to focus on here is really the explanation as well. So it's one thing to know what the correct answer is, but being able to express that very clearly is very important, especially for physics as well. Only about 10-20% of our questions in the VCAR final exam are not calculation or multiple choice, but explain questions. But these ones we have to make sure we do very well because they're the hardest ones. So Eric, if you don't mind flipping to the next slide, we'll go through what the key things are for this one. So the first one is obviously to understand the forces, right? How the magnetic forces work. And like I said, the explanation for our explained questions. And the second part is in terms of answering it, we need to know three things, okay? So the first one is you want to reference the right-hand grip rule when answering these answers, these questions. And the second one is utilizing the right-hand palm rule and understand that very well as well. And the third one is actually very important. You have to also talk about the Newton's third law, okay? So let's try to construct a very good response. I'll try to jot down the main points first, and then Eric can maybe, give us the proper answer later in the next slide. So I'll jot down the main points for this one. And if you look at the diagram, right, the first thing to do is to identify the direction of the current flow, okay? So the current flows to the right. All right, why does it flow to the right? Because the electrons are going to the left, okay? Electrons going to the left means that the conventional current, which actually tracks an imaginary positive charge flow, is going to the right. The long line is positive, the short line is negative, okay? The way I remember it is the long line can be broken up into two smaller lines to make a plus sign, whereas the shorter line is just a negative sign, right? So keep that in mind. So the whole thing the current flows in an anti-clockwise direction, and so it goes up and then enters both the tubes going to the left. So essentially what you have is you've got two wires, right? And both of these wires have current running to the left. So we call this a parallel wires, okay? If you have current or current carrying conductors that run in opposite directions, we call this anti-parallel. And we'll talk a bit about the patterns that we want to remember when we deal with these types of questions. So in the short answer, the first thing you want to write, guys, is you want to talk about the answer, which is, just give the answer, which is the tube that jumps upwards first is tube B. So we can say tube B jumps upwards. Okay, so that gets us 1 mark. The second thing is you want to go in and analyze the situation starting from the top wire. So if you look at wire A, okay, starting from tube A, you can use the right-hand grip rule. So use the right-hand grip rule on tube A. Your thumb is going to the left, okay, and your fingers wrap around the current so that your fingers above the wire is going into the page, okay? If you all guys do this with me, right? Your thumb is going to the left, your fingers above the wire goes into the page, and then it comes back towards you below, right, the wire A, right? So we can draw this into the diagram. So in blue, your magnetic field goes into the page above the wire, so it's into the page. And below the wire, your magnetic field comes out of the page. So we've got dots here, so out of the page below the wire. Okay, so we want to say that in your short answer. And then the next part is you use the right-hand palm rule, right? So here we start with the right-hand grip rule, okay? And then we say that in the vicinity of tube B, the magnetic field is coming out of the page. And now we use the right-hand palm rule, okay, on tube B. So if you focus on tube B now, that's the bottom tube, okay? Well, you can use the right-hand palm rule this time, right? Your right thumb is going to the left, and your fingers are coming towards you out of the page, right? I've got dots there as your magnetic field that's out of the page. And so your palm is now facing upwards, and therefore your magnetic force is also facing up. So we can use a green color to show that FB, the magnetic force, is going up. Now, the final thing you have to say is you want to talk about the Newton's third law, right? So you can say, therefore, because your FB, right, on tube B is upwards, you can say that, therefore, according to Newton's third law, which is every action has an equal and opposite reaction, because A is pulling B upwards, B is also pulling A downwards. And since B doesn't move, B can't go down, because remember, it's got two wooden pegs here on the sides to stop it from going down. If A can't move down, the only thing that can move is tube B, which moves upwards. Okay, so that's the main explanation. Now, any questions, guys, from you guys before we look at the better written solution? Okay, let's take a look, Eric, at the next slide. So we'll move on to the next part. So again, we start with the fact that the answer is tube B jumps upwards. That's number one. The second thing we talk about, guys, is the currents on both tubes A and B are going to the left. And we use the right-hand grip rule first. So we talk about the right-hand grip rule, okay? And around the tube A, your magnetic field comes out of the page, okay? Near the vicinity of tube B, okay? It's out of the page. We've got dots here. The field lines come out of the page. And then the next thing you talk about is the right-hand palm rule. So, and then you say, according to the right-hand palm rule, then tube B experiences an upward magnetic force, and therefore jumps upwards. You have to finish by saying Newton's third law states that every action has an equal and opposite reaction, which means that tube A would be pulled downwards. And then since tube A cannot move, right? Tube A is like the wooden pegs are there, right? It can't move down. The only thing that moves is tube B that goes upwards, and this completes your argument, okay? So I think some students gave me some very, very good detailed answers. I'll take a read later. So fantastic job to you guys for doing that. Again, any questions, happy to answer. Otherwise, move on to the next section. Cool. Let's move on then, Eric. The next part. Cool. So I think that's all we have time for. We've still got, I think, 2 SAQ questions towards the end. Feel free to try those out by yourself at home and look at our solutions that we'll send out later today. Eric, I'll hand it back over to you to finish off the webinar.
Fabulous. Yeah, I hope everyone has enjoyed, so far, the webinar about fields. It's a very complicated topic, as many students have told me, it's very hard. Hopefully today we clear up some misconceptions and you get more confidence, after joining today's webinar, especially for those who have Fields SAC in the future. So for the new students, you're more than welcome to book a free academic consult with us. So if we can provide some feedback to understand your goals and situation, and provide some recommendations as well, please scan the QR code. And I think Ralph, if you don't mind, put down the link to the registration. You can just click on the link and book in a time slot with us, and that's for the new students joining today. Afterwards, we started to develop many social media today, so hopefully you guys are aware of that, right? So we got a YouTube channel running with very high quality videos putting onto that. Facebook, if you only use that. Instagram is more the popular option, so please, it's free. We give out content for free, online, and for the next webinar, that if we work on it, we'll notify, on socials. So don't miss that. If we have any other future events, free webinars or materials for our subscribers, and I think starting for this year, Ralph, we're going to launch more blogs, written for the students, especially the ones about how to run investigations, right? So if you are doing VCE in Unit 4, then you're going to do investigation. How do we approach that? So we're going to have blogs and insights about that. So please, just click on the subscription button and do keep abreast of our websites as well, because we post all the materials in there too. And one last request is that if you find today's webinar very helpful, Ralph, would you like to walk through this Google review as well?
Yeah. So
I'll let you
in
have to
Google
talk
reviews,
about
if you
that.
want to leave a review, happy for you guys to do that. You don't have to, okay? But it's there. And yeah, if you guys again want some guidance, you find physics a bit hard, happy to answer you guys and help you guys out in the upcoming SAC. So pretty much all the SAC questions that in your school that you would encounter, we've pretty much seen all of them. And in our lessons, we specifically tackle doing these questions. So we find the most common, the questions that are guaranteed to come up. It's the same questions every year, all the differentiator questions for every SAC, just like the Fields one today. We'll make sure you guys are very well prepped for all of these kind of SAC questions for the upcoming year. So definitely something that, if you're interested in, do let us know and we can talk. But yeah, I think that's pretty much it for us today. Happy for you guys to stay behind and we can do a quick Q&A to answer any questions you guys have for us. And yeah. I think I've got a few questions via DM, so I'll start answering those, Eric. And
no worries. And for those who are gonna have a SAC, when you're back to school, all the best, right? We're with you on this one. So if you manage to see any interesting questions as well, feel free to send them to us. If you say, hey, Eric, Ralph, we got the same exact question in SAC. Well, congratulations, you just prepared for that. So all the best, and yeah, enjoy the lovely holidays. And I'll see you in the next webinar.